Well, hello. I'm Roy Salisbury, and welcome to beautiful Calgary, Alberta, Canada. I'm here today at the Flowserve facility, where they do all the engineering for the dry gas seal support systems. Now, most of you are here through the QR link we embedded in our recent paper on dry gas seal booster systems. Now, before I turn this over to the Flowserve team, keep a close lookout for the Flowserve's Ampliflow system's ability to handle changes in mold weight as well as labyrinth damage through its variable speed capability. So let's turn it over to the Flowserve guys.
Welcome to the Flowserve engineering facility for dry gas seal control panels. My name is Luis Figueroa, and today we're going to perform a test to demonstrate the operation of the Ampliflow system. Here we have a testing panel that shows the operation of the Flowserve Ampliflow system. The main parts of the system are inlet that allow us to review the pressure coming into the panel, dual coalescing dry gas seal filter with a transfer valve, Ampliflow booster with a solenoid electrically operated, a control valve to simulate different types of operation of the panel, a gauge to monitor the pressure at the outlet of the system, and an air receiver that simulates a compressor cavity, as well as a gauge to monitor the pressure on the air receiver. In terms of the air system, we have a filter, as well as mufflers that allow the air to exit the Ampliflow. We also have gauges to monitor the pressure in different points of the system, as well as a mass flow meter, as well as a controller for the Ampliflow system.
The following is a sketch for a typical dry gas seal tandem seal design. Primary seal gas supplied during set-out conditions is often supplied from an external source such as nitrogen or fuel gas shown in the sketch. As the dry gas seal leakage is minimal, virtually all the seal gas enters the process loop across the gas side labyrinth. Primary seal gas can, during set-out, also be supplied by the process through a dry gas seal booster system such as the Ampliflows. A typical process system includes both suction and discharge separators, cooler, and anti-surge valve circuit. For this first demonstration, the yellow tank will simulate the compressor process loop. An external primary seal gas will be injected into the loop using the Flowserve plant air, in this case using the nitrogen supply connection. Naturally, the rate of increase in pressure is a function of the clearance and number of teeth in the gas side labyrinth, the volume of the loop, and the time the compressor is idle, setting at set-out conditions. As expected, the loop pressure increases. Now in the field, the pressure will continue to increase until the relief valve in the suction separator lifts. Also, during this period, the process loop is being contaminated by the primary seal gas external supply. Both may require additional plant flaring to achieve a pressurized start and flaring to evacuate and replenish closed process loops such as refrigeration and hydrogen recycle. In the worst case, process catalysts may be damaged and require replacement. For the second demonstration, we will put the Ampliflow in service. The Ampliflow start signal will be initiated from a compressor normal shutdown or trip and run continuously as the compressor coasts down to 0 RPM. Now during set-out, the Ampliflow suction will then be taken from the actual process. Again, the process loop pressure begins at 58 psig set-out pressure. However, as the Ampliflow continues to operate, the process loop pressure does not increase. For compressor strings where pressurized restart is limited by set-out pressure, no plant flaring is required, thus resulting in faster restarts after spurious plant trips and no environmental issues associated with flaring. Also, since there's no external seal gas injected into the process loop, there's no risk of contamination of the loop, thus eliminating additional flaring and the cost of refrigerant replacement, again reducing the time required to achieve full on-specification production. Finally, in the case of processes that utilize a catalyst to achieve design production, the risk of damaging the catalyst is eliminated, as there is no external seal gas source. Again, an easy cost justification to utilize an Ampliflow. As discussed in the paper, the Ampliflow may be required to operate on different mole weight gases as the compressor commissioning moves from site piping leak checks utilizing nitrogen to operation on, say, propane. Additionally, many compressors utilize non-abradable gas-side labyrinth designs that are susceptible to damage as the rotor passes through the first critical speed. The following demonstrates how shaft movement can damage these types of seals. When labyrinth damage occurs, increased flow is required from the booster system to achieve the required labyrinth velocity to fully protect the dry gas seal faces from foreign object damage. In this final demonstration, we will show the Ampliflow's variable speed capability to step up and provide an increase in flow to account for the labyrinth damage. This allows clearing of the low seal gas permissive to start the compressor while protecting the seal. The Ampliflow's variable speed capability is demonstrated here. This increase can be easily programmed through the HMI.
Okay, so to summarize, we've shown a relatively low-cost piece of equipment that has a huge effect on the plant's flaring, availability, and operating cost. Well, thank you for the time, and thanks to the Flowserve team for providing the support to produce this video. We'll see you next time.